Thank you for joining today's presentation. My name is Huang. Today, Suravee and I are going to talk about a new hardware-assisted VIOMMU technology offered by AMD. Here is the agenda for today's presentation. At the beginning, I will give a brief overview about AMD IOMMU and how does DMA-Remap works in this hardware. For VIOMMU support, inside a guest VM, there are two types of the VIOMMU. The first one is QEMU emulated VIOMMU. We also know as software VIOMMU. And the second one is the core of today's presentation, is a hardware-assisted AMD VIOMMU. In the rest of presentation, Suravee will talk in details about the hardware changes for AMD VIOMMU and also the software changes in different system software components we are proposing. At the end, we'll open up the summary and for the discussion. Okay, so this slide shows you the AMD IOMMU design. As you can see on the right-hand side in the diagram, the hardware used a lot of different data structures for the IOMMU management. And the main registers are inside the two 4KB MMR region. The first 4KB contains, for example, base and config register. Those registers point to the starting address of those data structure. And the second 4KB MMR region contains head and tail register that point into inside those data structure. For example, the head and tail register into command buffer and PPR logs. The main functionality for IOMMU is to do the DMA-Remap. So AMD IOMMU support two types of IO page table. The first one is host IO page table. This is being used currently by Linux DMA-API and VFIO. We call this page table V1 page table, and this table does a translation from GPA to SPA. And the second page table is a little bit different. It's called V2 table, and it does support the x86 CPU page table format. This page table is currently used by Linux KFT driver. So as we know, IOMMU offer a lot of benefits. You can do device pass-through. You can enhance the IO security by using DMA isolation. So over the time, end user or customer always want to enable this feature for their guest VM. To support this feature, over the past several years, the community has come up with different solutions based on different device model. For example, we do have Intel IOMMU support in the QEMU. Similarly, for ARM SWMMU, we have the same capability. For AMD IOMMU, we do support pass-through for the emulated device. But for the VFIO PCI pass-through, this project is still work in progress. Recently, we just submitted a series of patches to enable this feature. To use this feature, it's very simple. When you start the QEMU command, you just specify AMD IOMMU device and add the VFIO PCI host device and attach to this AMD IOMMU. And that should be it. For pass-through device inside a guest VM, they can actually be classified into two categories. In the next slide, I will talk about why we differentiate them from each other. The first category is called emulated PCI device. For example, like Intel E1000 NIC, right? Inside the guest VM. And the second one is PCI pass-through device, like VFIO pass-through device. For example, you want to pass through a 40 gig NIC into your guest VM, and in the guest VM, you want this device to be managed by AMD IOMMU driver. Both devices are supported and for the DMA remapping and interrupt remapping. Next one. But the implementation for DMA remapping actually are a little bit different. As you can see on the right-hand side, for emulated PCI device, all the DMA coming up will be managed by emulated IOMMU. And this emulated IOMMU maintain emulated host table that does a translation from guest IOVA to GPA. But for PCI pass-through device, because this device actually is managed by host IOMMU, the real IOMMU hardware, the software needs to create a shadow host table that does the translation from guest IO to SPA. Obviously, this shadow host table maintenance creates some performance hit. Imagine that anytime the guest IOMMU driver updates its page table, we need to reflect that change in the host shadow host table used by the real hardware. In the meanwhile, there are other performance hit. For example, we need to emulate guest IOMMU driver access to its MMIO. On top of that, the IOMMU command processing and event log, event and PPR log access also needs to be emulated. Combine those things together, we can imagine that the performance for PCI pass-through is not great. Next one. So to solve this problem, AMD come up with a new hardware-based approach. It's called HW-VIOMMU. This hardware new feature tries to solve the problem we just mentioned in the last slide. For example, for shadow host table, we want to utilize the nested IO page table instead. And for the MMIO register access, we want to allow guests to directly access those registers. In the meanwhile, the hardware, the new feature, create a private mapping, allow the hardware to access guest IOMMU command directly. So those new hardware features will solve the problem we just mentioned in last slides and will beneficial for end user who want to pass through the native device into the guest VM. There's ongoing development effort around different areas in the system software components, which will be covered by Suravee in detail later on. I want to go back a little bit about nested IO page table support. So this nested IO page support is different from shadow host page table support I just mentioned in the last two slides. In this new design, the guest IOMMU driver will use the V2 table, the guest table that does the translation from guest IOVA to GPA. And the host IOMMU actually will use a host table that does a translation from GPA and SPA. So you can imagine that this nested IO page table is very similar to CPU side of nested paging. So we expect this will be able to solve some performance hit we mentioned in the previous slides. Now, putting these two designs together, we create a hybrid system model. Depending what kind of pass-through device you're going to use. If we want to use emulated PCI device, we will go back to use the current software-based approach, the emulated IOMMU, that DMA goes through the emulated host table, as shown on the right-hand side, the top part. If end user want to pass through a PCI device, then they will use a nested IO page table. And that requires adding a new AMD-vIOMMU device model. So by far, I just give you a brief introduction about the AMD IOMMU and the hardware VIOMMU. The rest of the presentation, Suravee, will talk about the detailed hardware design and the changes proposed in different system software components. Suravee?
Hi. So in the next section, I will start discussing the detail of the changes for the hardware-assisted VIOMMU feature. Starting with the hardware changes, we're introducing the IOMMU private address space. This address space is used by the IOMMU hardware to access per guest IOMMU data structures. On the left-hand side, there's a diagram showing the layout of the private address space. And you can see, starting from the top, we have the event and PPR lock, the command buffer, and the guest MMIO registers at the bottom. Also, it is used to access the VIOMMU specific data structures, which are the domain ID mapping table that maps the host domain ID to guest domain ID, and the device ID mapping table that maps the host device ID to the guest device ID. And this is for the pass-through device, the PCI pass-through device that used the VFIO. Also, another data structure is the command buffer dirty status table. And all the mapping here is being done using the IOMMU v1 page table that maps the private address to the system physical address. And it can support up to 64K VMs. Next hardware changes are the introduction of the VF and VF control MMIO bars. So the bars are used mainly by the hypervisor to access the per guest MMIO registers. As Wei mentioned earlier, we have two sets of MMIO registers. One is used for control, and another one is used for head and tail pointers of the data structure inside IOMMU. So the control one is basically accessed via the VF control MMIO bar. The pointers ones are accessed using the VF MMIO bar. And the diagram on the right-hand side just shows the breakdown of the regions of the bar. You can see that it's split into different 4K regions indexed by the guest ID. Same for the VF control MMIO. So next hardware change are the introduction of the new IOMMU commands and events. For the event, typically when an IOMMU encounter an error, it will generate event locks into the event buffer. And in this case, when we have the guest IOMMU, the errors inside the guest will actually be locked in the host IOMMU. So in order to be able to identify that the event belongs to the guest, we're introducing bit fields for the existing IOMMU event, and it listed here. So next will be the IOMMU host driver will process the event lock, and if it wants to inject that event into the guest, it can do so using the insert guest event command, which will place the event into the guest event lock. And another scenario is when we run into errors that related to VIOMMU specifically, the hardware will lock the VIOMMU hardware error event. And usually this will cause the guest to fail. And when we try to reinitialize and recover from that failure, there's a command to reset the VMMIO. There's a command called reset VMMIO that will reset the guest MMIO registers. Next are changes to the host IOMMU driver. And starting from the boot time initialization, First, we add the logic to detect and enable the IOMMU feature in the hardware. Then we set up the IOMMU v1 page table for the private address mapping. The first part also requires allocating and map the tables that listed here. We have the domain ID table, device ID table, and the command buffer 30-bit status table. And those are listed on the right-hand side here for the boot time. Then we have the per VM initialization code that is going to be used when we launch the VM. And basically, it will needs to create mapping for the private address to the SPA mapping. And that's basically the black arrows that shows here for event and PPR lock for command buffer, for guest MMIO registers. Also, we need to do host to guest mapping for the device ID and the domain ID. And we also need to set up for trapping when the guests try to access the first 4K of the MMIO region, which is the control regions of the MMIO. Also, we need to add code for supporting new IOMMU commands and events. So the next part are changes to the QEMU. Basically, the changes are introducing the new hardware IOMMU device model, which is different than the current software emulated IOMMU model. So on the right-hand side shows an example of a guest VM where we pass through 3 NIC devices. NIC 1 and NIC 0 is part of the IOMMU 0. And NIC 4 is actually on IOMMU 1. So when we pass through these 3 NICs into a same guest, we actually need to create 2 IOMMU instances and associate them accordingly, because the hardware has to be able to virtualize all the command buffers and all the data structure belongs to that the NIC is associated to. So this requires changes to several things in QEMU. The first thing is we need to be able to specify more than 1 IOMMU in a guest. Currently, with the emulated IOMMU, we only can support 1. We also need to be able to specify PCI topology for the VM and associativity with the device. For example, at the bottom here shows the command for QEMU to launch the guest with 2 IOMMU. The red one is for the IOMMU 0, and the green one is for the IOMMU 1. And to be able to support that, we also introduced new device-FS and IOCTL interface. The new device-FS is called AMD IOMMU, and this is implemented by the IOMMU host driver. Also, the new IOMMU specific IOCTL interface listed here to support all the operations that's required for setting up VMs, device, domain, and all the memory MMIO access that's needed to be trapped. The last part is the change for the guest IOMMU driver. As Wei mentioned, we now making use of the nested IO page table, which required the guest to be using the V2 table to do the guest IOVA translation to GPA, because the first table, or the V1 table is already being used by the VFIO to do GPA to SPA. The problem is currently for IOMMU driver, we only support V1 table for DMA-API. So we need to make some changes here for the guest driver. And the changes are split into 2 parts. First is to refactor the current code to use the generic IO page table framework that has been introduced and currently used by ARM. The code has been submitted upstream already for review. Next part will be adding support for the page table. for the V2 page table for DMA-API, and it's also going to be using the same generic IO page table framework. This is work in progress. So to summary, so far we've been comparing the software versus the hardware IOMMU and try to show how the hardware IOMMU is supposed to help improve performance for the guest IOMMU for the pass-through device by, instead of using the host page table, we're now going to be using the nested IO page table. And now guests can directly access MMIO register instead of having to be emulated by the hypervisor. Last part is all the emulation that needs to be done for command buffer, event buffer, and PPR buffer now is being accelerated by the hardware. So for the end, we would like to start some discussion with the audience around a few topics here. First is, we would like to get some feedback on the new hardware IOMMU device model that we are proposing. Second part is the hybrid IOMMU system model where we have both software and hardware IOMMU in the same guest. How that will scale and how would that be included in the QEMU? Are there pros and cons? We would like to get some feedback on that one. Next one is the IOCTL interface design, because we're actually using a brand new IOCTL interface. There were some discussion on whether we should extending the existing VFIO IOCTL interface or not. And for the last part, we would like to get some feedback on additional usage models based on the proposed design that we have presented. Thank you.